Okay, so section 9.6, going back to motion of a system of particles. You'll get your center of mass questions here and there for both sections, Physics 1 and Physics C. So it's good to have a core understanding of how this works. So if you recall, the equation for center of mass and along the x-axis is given as the collection of all the masses in the system and their positions. So mi represents each mass involved, xi is their positions, and m is the total mass of the system. So if you're on the x-axis, for example, and it's usually with respect to some origin, so you have mass 1, mass 2, mass 3, and you can just basically call it a coordinate, if you will. So you have m1, x1, m2, x2, and then say m3, x3. You can find the center of mass with respect to this position here, that origin, by using this formula. And so that becomes mass 1. Let's say that this is, well, I'll just write up the formula itself. Over all the masses. And let's say this is 1, 2, and 3 kilograms, right? And they're 1, 2, and 3 centimeters. Keep it simple. So 1, so this is 2 kilograms and 2 centimeters. 3 and 3 over, what's that? 3 is 6. The total mass in the system. So 1 plus 4 plus 9 is 14. 14 over 6. That'll be the center of mass of that collection. So you guys remember that? Or anyway, the center of mass of the entire system is at 2.3 centimeters. So this is 1, this is 2. So somewhere right in here would be the center of mass of that system. Right, and if we use this formula for the x-axis, the same thing for the y-axis, and then also the radial position of the center of mass will be the sum of the center of mass in the x direction and the y direction and even the z direction, because that's a radial position. If it's 2D, it's x and y. If it's 3D, it's x, y, and z. And like if you're just dealing with a sphere or cube or something, right? So just to show that real quick. So on the y-axis, it's the same thing. If you want to find the center of mass along the y-axis, it'd be 1 over the collection of masses and all of their masses with respect to the y-axis. So again, so m1, y1, m2, m3, y3 over m. And let's just say the same positions again, 1, 2, and everything else in the same center of mass, assuming everything from above is the same, so we have the center of mass 2.3, and you can make this anything you want. All right, so and it's generally with respect to some origin, because you're trying to find the position with respect to something. If you don't have a reference point, it's like what are their positions, relative positions. So that goes back to first principles, where we're always trying to define a position in space relative to some reference point, starting point, and the same logic here. So if for example, if I want to find the center of mass of the system, and I use this as my reference point, well, then this is going to be, it's going to be same, because this is going to be 1 meter away from here. If this is my starting point, the second mass is going to be 1 over here, and then this position will be 1 to the right. So still be along, you know, so still be a positive position, even though it's left, it's position. Remember, it's not, you know, displacement, but even still, it's still on the positive x-axis. So this would still be 1 times 1, and this will be 3 times 1 divided by 6, and you will get the same center of mass, no matter where no matter where your reference point is. In this case, the easiest case is the origin is your starting point, or you could have one of the masses be your starting point and get the positions with respect to that mass. If mass 1 was your starting point, you can get their positions, and then, you know, so forth. So if mass 1, for example, was your starting point, it would be 1 times 0. Nothing there because that's the origin. And then this will be 2 times 1, and this will be 3 times 2, because now 3 is 2 meters or 2 centimeters away from this guy. Does that make sense? Questions? Center of mass? It's old hat. We saw a long time ago, chapter 9, but hopefully those basics are easy to follow. But if you know, obviously, if there's questions, always speak up. And as I mentioned, the third thing, the radial position for the center of mass would be the sum of all of them. And the unit vector notation is just basically saying that the center of mass along the x-axis indicated by this I hat notation, and then y, and then z, or you just say Ri is xi plus yi plus zi. This is the same thing. You're just being very specific and detailed by saying that the position of the center of mass radially is the sum of all of the center of masses along their respective axes, indicated by the unit vectors I, j, and k. So then further representing that in our standard notation, this would be m, I, r, I. So if we have some r vector that's consisting of x, y, and z positions, or you have some say R1, it's 2i hat plus 5j hat, and you have a mass that is in space. You know, it's basically looking like this. So you have some r that has this coordinate 2 and 5 basically, right? That would be 5, that would be 2, and the radial vector would be the linear combination of x and y. And so this will be what you put in there. So if that mass was like 3 kilograms, it'd be 3 times 2 I hat plus 5 j hat, and then you had another unit vector, or you had another mass, and a unit vector was like, say, 4 I hat plus 7 j hat, and then divided by the total mass, which would be 8 kilograms. So you could find the radial position of the center of mass using that, because remember, this is R1 and this is R2 from here, because remember, MI represents each mass and RI is each radial vector, which is a sum of at least X and Y, and it could be Z out there as well. Does that make sense? Instead of just one axis, we're doing both at the same time, X and Y, or we could even do all three, X, Y, Z. Put in a 7K hat or whatever, you know, just depends. Okay, so that's the back to the center of mass and stuff. So now let's extend that to the velocity of center of mass, and even momentum of the center of mass. So we're talking about in section 9.6, we're talking about the motion of a system of particles. And so we're not just dealing with positions, we're going to get the velocity of the center of mass. So our fifth step, velocity of the center of mass. So we know what the center of mass is, we can calculate that. So what is the speed of that center of mass? So center of mass really is just, as if all those particles were concentrated to one point and they move as one unit, one velocity. You can determine the center of mass of that system as if all those particles are concentrated as one, and then you can even get the momentum of the center of mass, which is just the collective mass times the velocity of the center of mass. It's really, same logic. It's, not anything too peculiar. What we've seen contextually, right? So 1 over m, and so MIVI, right? So same stuff. If I want to find the velocity of the center of mass of a collection of particles, ith particle, I can have 2 or 100, the M1, V1, M2, V2, let's say, over M. And I can get my velocity of my center of mass, very similar to my positions of center of mass, right? Like in an explosion, you have a, bomb or whatever the case is, and then all of a sudden it scatters, it blows up, and you got particles going all over the place with all these velocities. What's the velocity of this particle? What's the velocity of that particle? All these particles together, because they were once as one unit. So then you can still, you can find the velocity of the center of mass as if it was still one unit. So it's all kind of like a conservation thing, but even as stuff is blown up, you can still figure out because the velocity of the center of mass will be as if it was still moving as one, kind of invisible, but it's, in the center of all of those particles moving at all those different velocities, right? And you divide that by the total mass of the system. Very useful in explosions, breaking up billiard balls on pool tables, all that type of action, right? And then the momentum of the center of mass, if you will, would just be the total mass times velocity of the center of mass, right? And that becomes just a collection of all of the masses and their velocities, which is equal to, this is momentum, right? Sum of all the individual momenta. So the total momentum of the system, right, is the sum of all the individual momenta. And that goes back to our definition of momentum in the first place. The total momentum of the system is momentum 1 plus momentum 2 plus momentum 3, indicated by this. And then you set those guys equal to each other, knowing that the forces that exist between them are all internal. There's no external forces. And so we get a conservation of momentum, especially if we just had like 2 particles here, or 10 particles, it doesn't matter. 10 particles on the initial stage, 10 particles on the final stage. Add them together, that's the total momentum, and that's going to be a constant. Never changes, because the forces involved are all internal and they basically cancel out. Does that make sense for these formulas? Cool, great. So it's really a basic concept of, you can also think of it like all these particles scattering, and you're like just observing everything at once. You're the center of mass. Everything is relative to you. Or you can be the first particle and you're looking at all the other particles. You're the center of mass. No, I'm the center of mass. It's all relative locations. Constant, sorry. Let me rewrite that. So yeah, equals P total. It's conserved. The total energy of the system stays a constant. Total momentum constant. All right, so let's do an example. Let's made this up. Okay, so let's say we have our first mass, so I said 17 kilograms, and then our second mass is like 3, and then the first mass is moving at a speed of 3 meters per second, and the second mass initially is 0, it's at rest. I say then that the final speed of the second guy is going to be 7 meters per second because he's small. He's going to shoot off, faster. What is the velocity of the first mass after? So we can use conservation of momentum, M1, V1, initial. Okay, M1, V, final. And this guy was at rest, so he goes away. So I want to find the velocity of this guy last, because I want to figure out what is the velocity of the center of mass before and after. What do you think it should be? Whatever the velocity of the center of mass is before and after, well, whatever the velocity of center of mass is, what's the relationship between before and after? What do you think it should be for velocity of center mass? Whatever the velocity of center of mass in the beginning, what should it be in the end?
Same.
Should be the same thing, because you're talking about one object moving as one. It's constant. It's, nothing changes. It's the conservation of momentum. One mass moving as with one velocity. Yes. The velocity of the center mass will be the same. We're going to prove it. That's our hypothesis. Oh, okay, we intuitively infer yes, it should be because conservation principles. Let's prove it. Let's see what that'll be. V1 final will be minus divided by M1. Right. So let's do 17 kilograms times 3, 3 times 7. And I'm assuming that they're going to be going in the same direction, because the larger mass, I mean, they're both going the same direction after, but the larger mass is going to move slower. That's like an inference, bigger mass move slower, smaller mass move faster. I just gave these, numbers here. And so this is 17. So this will be 51 minus 21. This becomes 1.76. So the big mass in the end moves at 1.76 meters per second. So let's say that's if I find the velocity of the center of mass in the beginning, and that'll be, of course, the collection of all the particles, M1 V1 plus M2 V2, and this is all initial, and then over M. Well, this one is not moving, so 17 times 3 over the collection of masses, which is 17 plus 3. This is 2.55 meters per second. So the center of mass, and that should make some sense to you, because I didn't draw it. But big mass, small mass, collision, big mass still moves at 1.76, small mass at 7. So if he's 3 in the beginning and he's, nothing, you can kind of, inferentially see that the center of mass will be somewhere in the middle. Center of mass is not going to be necessarily exactly in the middle, but in between the collection of particles. So somewhere, in the bounds And then in the end, that 2.55 will be the same, a conservation of momentum, because we have the same, we have the same mass before and after. So the center of mass will be the same before and after. And if you don't see that, we can prove that. So in the end, it goes 17. So again, so M1 V1 final, 2 V2 final, and that goes 17 times 1.76 plus 3 times 7 over 20. And you'll find that that's roughly the same as like 2.54 something or other. But yeah, so you can prove to yourself that it is the same. Plus 2.546, 2.55. So yeah, I mean, it's good because like I've seen problems come up even physics 1 and C where you get a random couple of center of mass relationships. So it's good to have the basics of that, how to work it. And we'll do a couple more examples here. Okay. Everybody have that so far? So before and after, we inferred it should be the same theory, and Sin, you're right. It's experimental. We calculated it's the same. All right. Okay, so we're now going to go to example 914 and take a look at this guy, an explosions problem. Let's see. A rocket is fired vertically upward. At the instant it reaches an altitude of 1,000 meters and a speed of 300 meters per second, it explodes into 3 fragments having equal mass. One fragment moves upward with a speed of 450 meters per second following the explosion. The second fragment has a speed of 240 meters per second and is moving east right after the explosion. What is the velocity of the third fragment immediately after the explosion? Okay, so we have rocket in the beginning phase. We can say J hat initial or whatever nomenclature put, that's going to make it easy for you. But this is saying a velocity in the y direction in the initially is 300 meters per second. Then there's an explosion, and then we have one guy, VJ final, and one guy on the going in the y direction final in the aftermath at 450 meters per second, and then this guy is along the x-axis at 240. And what about number 3? What about the speed of the third guy? I had some bunch of stuff over there, but I think we don't need to be redundant there. So again, the classic case of momentum in the beginning equals momentum in the end. And so we have a collection of momenta, along the x and y axes. So we can sum everything together, x and y, to make the case of the momentum in the beginning phase, which is going to be equal to the x and y momenta in the final phase. And so what we have, in the beginning, it's all one unit, so it's going to be the total mass times 300 Let's see that there. So in a J hat, and we know that's initial. And then there's 3 fragments, so it's going to, you know, each of them is the same 3 fragments is going to break up into thirds. So we have one mass that's a third of the original moving east at 240, and then one moving north and at 450. And then what about the velocity of the last mass? So again, it's just algebra at this point. You know, solving for V final. So we can just subtract everything on the other side, and we'll have M300 J hat minus M3 240 I hat minus over 3 450 J hat. So let's get, you know, we have the fraction there, and these masses go away. So it's going to, you know, multiply by 3. This is going to be 3m, and then that's just going to be m. That's going to be m. Then the masses go away. So we just now have V final equals. So we have these 2 terms. So this 3 times 300 is 900 minus 450 is just positive 450, and then the remaining negative 240. So the velocity of the third fragment is going to be a linear combination of minus 240 along the x-axis plus 450 along the y-axis. So it's going to be moving at an angle, and those are the coordinates. Well, it's going to probably be moving, yeah, it's going to be moving like south. Okay, so it's negative 240, so it's going to be south, like southwest. It's got a negative x and a, oh, okay, your orientation right. So it's going to be kind of like northwest, because we have a negative x and a positive y. I mean, again, we know it's going to be a sum of the 2. It's going to be a radial direction for mass 3, which should geometrically make some sense, because one's going y, one's going x, and the third one's going to be the sum of the 2 to, you know, for conservation. But yeah, that's just, you know, a bit of intuition there, but yeah, that should hopefully make some sense why that's radial. Okay, so 1, and then 2, and then, you know, so sum to sum up to, and the Pythagorean sum gives you the magnitude of what it is in the beginning, 300. So sort of thing. But any questions on that example? Why we started off with the, because the momentum, you know, the momentum could be all radial. Remember, it's one big particle that's moving as one. If it was moving radially along x, y, and z, it'd just be x, y, z, or ijk equals ijk, you know, on the right-hand side. But at the end of the day, when we do have multiple directions, we can treat everything as a sum of these vectors. Just like with the r vector, we have ijk equals another ijk. Okay, so I will do that. How about you guys do an example problem? Try number 41 on page 264. a few minutes for that. So they want you to, find this velocity of center of mass. So 2 kilogram particle has a velocity of 2 I hat minus 3 j hat. So it's like, it's moving radially. 2 and then down 3 radial. And a 3 kilogram particle has a velocity of 1 and 6, 1 I hat plus 6 j hat. So it's like going the other way, radially. Find the velocity of the center of mass and the total momentum of the system. Okay, so V1 is going to be a combination of those two. So M1 V1 plus M2 V2 divided by total mass. Now I give you the velocity of the center. And then total momentum is just the total mass times what you get in A. And that'll be our stuff on that. We could do 44, but it's kind of out of context. We haven't seen we haven't seen problems where we know the velocities in the beginning, like in 44, both of them, but in the end, you don't know any of them. So there's a trick. There's a formula that you can use to set the velocities, the velocity of the first mass initial final plus second mass initial final equals second mass initial final, and you can get an expression for one of the variables back substituted into the conservation momentum, and then we don't need to do that. So 41, we'll keep at that, and 42 could be something that the C people could do. We'll just keep simple. All right.